Hello students, welcome to this new lecture. In this lecture we will discuss about the introductory part of Riemann integration. So here is the definition. Let us consider fx is a function that defines on the closed interval ab, and this is said to be a Riemann integrable if there exists the partition in the interval. As you can see, the function that started from a and ending at b, this is the initial and at a, and this is the ending point, that is b. Okay, so it means that there exists partition. As you can see, there is a partition from this to this and this to this, and this is another partition. So there is a nth partition that exists in between the interval, in between the closed interval ab. Okay, so it means that here is the description. Let a b is a closed interval, be a given interval at a finite set p consisting of points a is equals to x0, x1, x2 up to xn is equals to b. So this is the initial position, and this is the point where x started, and this is the x0 point. Okay, and this is the first partition will be known for x1, the second one is x2, and there is a nth partition, and this is the ending partition, and this is to be called as xn. Okay, so a is equals to x0, this one, and xn is b, and there is a nth partition. Okay, so here I have done there is 6 partition from x0 to here this is x6. Okay, this is the first partition, second partition, third partition, fourth partition, fifth and sixth. Okay, so the noted thing is the partition the length of the partition may vary. They doesn't equal at they may vary, the partition that x0 to x1, the length of this partition may not be same in on every partition, right? So if the partition, this one is little longer and as compared to this one. Okay, so the partition are vary in different stages. So how can we write the partition? Like in the interval ab we have points like x0 to x6. As you can see, x0, x1, x2, x3, x4, x5 and x6. Okay, and this can be written as like a is equals to x0 and less than or equals to will applicable here, because as we started from 0 as we started from lower to higher order, like 0, 1, 2, 3, 4, 5 and 6, so we always use this symbol. Okay, and as we are here using this equals because somehow the partition is very close to the another partition. That means suppose x2 is here is very close to x1, so in these cases the partition is nearly equals. So in these cases we are using less than or equals. So here I have arranged this: a is equals to x0, x less than equals to x1, less than equals to x2, and so on up to x6. Okay, so the thing is the gap between the partition length may not be same, as I told you this. And here we are discussing the sub interval. What are the sub interval? So in this big interval we must have sub interval, like this is the another interval. If we close this bracket here, so this is one interval. Again this is one interval, x2 to x3 another interval, x3 to x4 another interval, x4 to x5 is another interval, and similarly this is the end interval. So there is a sub interval between an interval. So the intervals are like x0, x1, x1, x2, x2, x3, x4, x5, x5 and x6. Okay, so the sub interval can be written as del xi, where I is equals to 1, 2, 3, and del x1 is equals to this position is del x1, that is the x1 minus x0. Okay, And the similarity, x1 x2, there is another interval, and it is known for del x2, and del x2 is equals to x2 minus x1. So similar, this one is del x3 and x3 minus x2, and del x5 minus x4. Here is x4 minus x3, this is x4, this is del x4, this is del x5, and this is del x6. Okay, as I have mentioned all the interval and the difference. Okay, so the total difference can be written as, and this will be x1 plus del x2, del x1 plus del x2 plus del x3 plus del x4 plus del x5 plus del xc, and this is equals to the whole difference, that is from a to b. Okay, and the difference can be written as b minus a. Okay, now coming to the next diagram, as you can see here, the function that started from a and that ending at b, and this is the function. Okay, so there is a partition, like there is 6 partition from x0 to x6. Okay, so as you can see here, there is partition, and here I have done some of the rectangle. As you can see here, we just need to find the value, and we just noted it as a partition. So this is like, as you can see here, this is capital M1, this is small m1, because how to write this? Okay, so let me explain you. The value of m1 is equal to infimum of, this is the infimum of fx, that varies from x0 to x1. So it means that from this to this is like x1 minus x0. Okay, this is x1 minus x0, and the lowest height from the interval, like this interval, this rectangle, in which position the height is minimum, so that is the small m1. Okay, so in this position, as you can see here, from this position to this position, this is the position where m1 length is minimum. Okay, so this can be written as m1 is equals to infimum fx and x0 less than x less than equals to x0 less than equals to x less than equals to x1. Okay, so similarly here from x1 to x2, as you can see here, the function varies from this to this, and there is a down curve. Okay, and this is the point from where we find the minimum height for m2. Okay, so we cannot treat as this this is a m2, this is not m2, this is the highest from this interval x1 to x2, and the highest can be treated as capital M1, and the lowest can be written as small m1. Okay, so this is the lowest height, and it can be written as small m1, small m2. Okay, so this is the m1, this is the m2, and similarly from x2 to x3 interval there is small m3 and m4, m5 and m6 as well. Okay, so here I have done all this m1 to m6, and this is called the lower partition, because the partition, the rectangle, as you can see, this is inside the curve, the upper partition can be if I do the upper partition, so this is the highest point from x0. Okay, and if I done this, like this is a rectangle, so this partition is a highest partition. Okay, and this is the lower partition. Okay, in similarly in these cases you can this is visible again, and this in this one again, this one again okay, this one. Okay, so these are the upper partition, these are the lower partition, and this upper partition can be written as UPF and the lower partition can be written as LPF. Okay, so LPF, that means the lower partition, and this can be written as M1 del x1. So that means the lower partition can be written as small m1, and del x1 means this is the area, that is del x1. So del x1 plus small m2 del x2 and up to m6 del x6. Okay, and this can be written as summation of I is equals to 1 to 6 mi del xi. Okay, so I is equals to the interval, total number of interval, that is 6. Okay, m6 x6, and LPF is a lower Riemann sum or a lower partition of the function. It is a lower partition of the function. Similarly, M1 can be written as supremum. So infimum means the lower partition, that means that inside the function, and upper partition, that upper side. Okay, this is the lower side and this is the upper side. So this is for upper side we use the supremum, for lower side we use the infimum. Okay, and the partition is same for every for small m1 and capital M1. The partition is same because we find the lower partition inside, lower side for infimum and upper side for supremum. Okay, so similarly the upper partition can be written as U of PF, that is upper partition of the function, is equals to, this is can be written as capital M1 del of x1. Okay, so as here we write small m1. Okay, but here we use capital M1 as we use the upper partition, that means this one the upper partition. Okay, and the formula is this is equals to summation I is equals to 1 to 6 and capital Mi and del xi. So the upper partition is upper Riemann sum of the f of partition f. So it means, and mathematically lower partition is less than and equals to upper partition of the function. That means lower partition is always less than and equals to upper partition of the function. So okay guys, so the upper partition means not this much, total is the upper partition and the lower partition is only this much. Okay, I hope you understand. The upper partition, that means this one total rectangle from here to here, and the lower partition is only this one. So it means that the upper partition is greater than, always and greater than equals to this one. Okay, the lower partition. So this is the one, and this can be written as upper partition of the function, that integration a, this is the lower partition, fx dx is equals to supremum LPF, P is a partition A on the closed interval, AB is called the lower integral of the function over closed interval AB. For upper partition A to B, and this is the upper partition, here is B. Okay, and fx dx is equals to infimum of upper partition, P is a partition A to B. So this is the introductory part of the Riemann integration. I hope you understand. So in the next lecture we will discuss some theorems related to this Riemann integration. Thank you so much for watching.